Okay, so let's start with Einstein. So Einstein made many very important contributions to physics, the different areas of physics, but there was one particular thing that he's very famous for, one equation that he's associated to, which is kind of more important than any of the others. I'm not sure if you guys know about this equation. This one? Not that one. This is the equation that is so important that it's referred to as Einstein's equation, not the other one. And what this equation says is it says that matter makes space-time curve. So this is the equation that describes the theory of general relativity. So you can try to make a picture of that, probably a picture that you've seen before. Here's what it means that matter makes space-time curve. So let's first start out with a case with no matter. Well, this is a picture of flat space and a couple of rocket ships moving around. And if we add some matter, you can see the space-time curve somewhat, and the rocket ships can feel the influence of the matter through the curvature of space, or more generally of space-time. If you add more matter, more suns, then the space-time is more curved. Rocket ships feel the gravitational force more. And if you imagine adding more and more matter in any given place in space, eventually the space-time will become sufficiently curved that there's a horizon that forms. And what the meaning of a horizon is it's a point beyond which no signal can get out. So the horizon is supposed to be represented by this black line here. And the idea is that nothing can exit this region here. Here, you might get sucked into the black hole, but if you have a sufficiently powerful rocket, you'll be able to stay away. But once you cross the horizon, then no matter how powerful the rocket is, you won't be able to leave the black hole. So that's a kind of a strong version of the idea that matter makes space-time curve. Okay, so here's a better picture of the same thing. We have this rocket. It's out here in the region where space, or more accurately space-time, is fairly weakly curved, but it becomes more strongly curved. And you can imagine that this line here is the horizon. Anything that passes beyond that point is doomed to fall into the black hole and will not be able to make it back out. Okay, so what does a black hole look like in real life, as opposed to these sort of fanciful drawings of curved space or curved space-time? So here's a somewhat fanciful picture of a black hole, and you can see this sort of distortion of the light from behind it, and that's a consequence of the curvature of the space-time between us and the stuff that emitted this light behind the black hole. But the last 5 years have been kind of an exciting time for people who work on black holes, because now we have more data, more real data about actual black holes. This here is a picture from the Event Horizon Telescope of an actual black hole. So it's not an amazing picture, but it's amazing in that it's an actual picture of a black hole. You can kind of see the dark region in the middle that corresponds to the actual black hole. Okay. So that picture was from a couple of years ago, but about 5 years ago, there was something even more exciting from perspective of many people who work on black holes, which is that there was a detection of gravitational waves from a pair of colliding black holes. This was the LIGO experiment, an experiment which detects gravitational waves, and they detected gravitational waves being emitted by a pair of black holes. So you can think of those as a couple of these objects, curved space-time objects. Each of them has a horizon. And you can imagine that if they get close to each other, they can attract each other. And generally, there'll be a little bit of angular momentum, so they won't just fall straight into each other. They'll kind of orbit around each other to some extent. Then eventually, they will form one black hole, one horizon, somewhat larger horizon, together with ripples in the space-time that emanate out from that point. Think about throwing a rock into a pond or something like that. There will be some ripples that propagate out. The LIGO detector actually measured these ripples in space-time. So this is an incredible process, and I want to show you a simulation from the LIGO experiment. This is a simulation of what that might look like. These two black holes that we start with are kind of orbiting around each other, gradually getting closer, and the process kind of speeds up as they get closer to merging. Then finally, the two horizons merge into one horizon, end up with one black hole and a little bit of radiation going off, flying away from this merger of the two black holes. Okay, so let's go back to this. This is a kind of a picture of the space-time after the merger. You have a new horizon which formed from the two original horizons of the two separate black holes, and some ripples emanating out. Now, this is an absolutely incredible process, which kind of boggles the mind in terms of scales of matter and energy. So to kind of illustrate this, let's do the following calculation together using that other Einstein equation, E equals mc squared. So by studying the detailed pattern of the gravitational waves, the LIGO team was able to estimate the masses of the two black holes that collided, also the mass of the final composite black hole. So what they believe is that the first black hole was about 36 times as massive as the sun. And the second black hole was a little bit smaller, but still quite big. It was 29 times the mass of the sun. And okay, so if we add those up, what do we get? 36 plus 29 is 65. So the initial amount of matter in these two separate black holes was 65 times the mass of the sun. The final black hole had 62 solar masses. So the mass of the final black hole was 62 times the mass of the sun. You'll notice that there's a difference there between 65 and 62. There's 3 solar masses that have gone missing. 3 solar masses have gone missing in this collision. Where did those go? Where did those 3 solar masses go? Oh, they were emitted in energy, exactly. So in energy, they were emitted in the gravitational wave, primarily emitted in the gravitational waves, were emitted during the final moments of the merger of these two black holes. As they're rotating around each other, they're emitting gravitational waves for a long time, but the power increases dramatically towards the final moments of the merger. And actually, a lot of the power, a lot of the energy is emitted, a lot of the 3 solar masses was emitted in the last 100th of a second in collision. So here's the calculation that blows my mind. Let's try to calculate how much power is being emitted during the final 100th of a second in this merger of two black holes, collision of two black holes. So power is what? Power is an amount of energy divided by an amount of time. So the amount of energy was emitted. Well, energy is mass c squared. That's E equals mc squared. So what's the amount of energy? It's 3 solar masses times c squared. So this is the mass of the sun, roughly. This is 3. We take this amount of energy, 3 times the mass of the sun times c squared. We divide it by the amount of time during which that energy was emitted. And that's about 100th of a second. Okay, so that's, well, that looks like there's some big numbers getting involved there. That's a good sign. I'm a high energy theoretical physicist. I'm not great with these kinds of calculations, so I put it into Google, and it spits out the following answer. This is the amount of power that was being emitted in gravitational waves in watts. Watts are a ridiculous unit to discuss this in. Like, watts are something that makes sense for humans and light bulbs and stuff. But well, numbers work, so we can express it in watts. It's about 10 to the 49 watts of power. So, okay, that's a big number. What does that mean? That a lot. So let's try to compare it to something. A star like the sun emits about 10 to the 26 watts of power. Pick this up. I didn't calculate that. Most mainly invisible light. You need the stuff that we can see when we look at the sun. the total amount of power that the sun is giving off is around 10 to the 26 watts. Okay, so that's not big enough. We need more. Well, it so happens that there's about 10 to the 22 stars in our observable universe. 10 to the 22 stars in our observable universe. If we take all of the stars, that means stars that we have observed, I mean the number of stars that would be possible for us to observe in our backwards light cone. So the total power emitted by all of the stars in the universe is 10 to the 22 times this. Okay, so what is that? That's 10 to the 22 times 3 times 10 to the 26. That comes out to 10 to the 48. What was the black hole doing? The black hole merger was emitting 10 to the 49 watts. So black hole, these two black holes merging were briefly emitting more power than all of the stars in the universe. So this is it's amazing, right? That is absolutely amazing. So that is the reason why this is Einstein's equation. That process, that incredibly powerful process, boggles our imagination. That is something that we know how to describe, calculate using this equation. So that's yeah, please.
Your initial picture of a black hole
Yeah.
seems to imply that it has some dimension. What was the mass of that black hole, and what was its dimension, if that can be measured?
What does dimension mean? Sorry.
Well, just radius.
Ah, okay, good. So yeah, we can work that out. So the black holes had roughly 30 solar masses worth of mass, and the horizon of a black hole, the radius is proportional to the mass. And so the thing you can remember is that I hope I'm not saying this wrong. I believe that a solar mass black hole have a horizon, the radius that's about 1 kilometer. So these black holes had horizons with radius that's about 30 kilometers. What does the radius of a horizon mean? It means the thing such that if you compute the area, the thing is well defined as sort of the area of the horizon. And so this is the radius such that if you computed an area from it, you get the right answer. It's about 30 kilometers. So they're big as far as objects go. They're pretty small to be emitting more power than all of the rest of the universe at that time. Okay, so this is yeah. Another question? No. Okay. All right. So that's Einstein's equation.
The merger itself, the reason they don't just orbit each other forever is because of gravitational radiation, or
well, that would do it. That would do it. It might be that there's also like the black holes are not completely in empty space-time. There's some stuff around them, and that might contribute as well. I don't know whether it's that or whether it's a gravitational radiation, but either effect would be enough to cause them to spiral.
So the process of these two black holes going around and then merging, how long did that take?
Well, so it depends what you mean. It's a process that went on for a very, very long time. And for a very, very long time, they were just orbiting each other, looked like nothing much was going on. Looked like they were pretty much in stable configuration, orbiting many, many times. I'm not sure how long, but an extremely long time. And they were slowly losing energy, just a little bit, getting close to each other. And then most of the action, most of the good stuff happens in the very last 100th of a second in this merger.
Millions of years.
I'm sure that they were orbiting for much longer than millions of years beforehand. Like they were orbiting for astrophysical timescales, but most of the power was emitted in the very end.